Okay, hey everyone, thank you all for coming to this talk in which we'll talk about how we added the NVMe over TCP subsystem to the syscaller kernel fuzzer. A little bit about me. My name is Alon Zahavi. I'm a security researcher at CyberArk and mainly focus on low-level stuff and kernel fuzzing. The agenda for today will start with a bit of an overview about syscaller. Then we'll go over to NVMe over TCP overview. And finally, we'll add those two things together and show how to add NVMe to syscaller and fuzz it. Before we start, I want to give you a little sneak peek for the demo that will be later on. Here, I'm just starting the fuzzer process, and hopefully by the end of the talk, we'll have some bugs to show you. Let's start with syscaller. Syscaller is a coverage-guided kernel fuzzer that generates inputs using a descriptions that developers made inside the syscaller repository. And it uses kcov to collect the coverage data inside Linux machines. But of course, I'm not gonna give you just this high-level overview. So we'll talk a bit about the internals. On the screen, you can see, maybe you can see the scheme from the official repository on how syscaller works, and we'll break it down a bit. We first have the sysmanager process, which is the main part. This sysmanager obviously manages the whole fuzzing process. It also creates the VM instances. In our case, we chose to use the QEMU VMs. And it starts the sysfuzzer processes inside those VMs. The sysfuzzers are being monitored by the sysmanager. And they also execute sysexecutor processes inside the VMs. While each sysexecutor gets an input from sysfuzzer, runs the input and sends the result back up to sysfuzzer and then sysmanager. We also have something called syslang. Syslang is the language in which syscaller knows how to talk with us and with the kernel C programming language. So it looks something like that. We have a description written in syslang. We have the sysfuzzer that reads the description, and when it reads the description, it generates input to be executed later on. So, as I said, the descriptions are written in syslang. So let's learn about how to use syslang to create the descriptions. We'll start with the example of the read syscall. Here you can see the syscall definition as written in the Linux kernel sources. And below that, you have the read definition, a description to be exact, written in syslang. We first define the syscall name. In this case, again, this is just the read syscall. We describe the parameter type. On the Linux sources, you can see we use unsigned int, but in syslang, we use something called fd. Fd is just beautified name of file descriptor inside the syscaller repository. And lastly, we have the parameter name. Again, in this case, we just have fd. But sometimes we don't just want to use the regular syscall, and we want to make it more exact and to send some specific parameters. For that case, we have something called syscall variants. To create a variant, we use the $, which indicates a variant. And afterwards, we have the variant name. In this case, we have the variant my file of the read syscall. the specific parameter we send is this fd_my_file. fd_my_file is a resource that will be talked later on what resources are. And this is a specific resource that will always be sent when using the read my file variant. You also can see here the buffer type, which is a special type in Syz'ed. This is just a pointer to data that Syscaller will know to create when generating inputs. And we have the out here. The out indicator indicates that this buffer is an output buffer. So as probably you can already guess, when we send a read syscall, we don't send it with a populated buffer. We tell the kernel to populate this buffer and send it to us. So this is why we say here the out. And last but not least, we have the special len type that automatically calculates the data of the data parameter, which is the buffer we sent, when generating the inputs, and send it as a parameter to the syscall. So as I said, we have the resource fd_my_file, and from the documentation of Syzcaller, you can see that resources represent values that need to be passed from one output of a syscall to another. To create or to describe a syscall, a resource, we have the resource declaration with the name of the resource right after that, and which underlying type of resource it's derived from. In our case, fd_my_file, which is a file descriptor to a specific file, will be derived from fd. We use it as such. We start with declaring the resource, fd_my_file. Then we give it another syscall that will be returned into our resource. So here you can see the open my file variant, and you can see in the first parameter that it will always open the my file on the root file system. And to make the open variant to always return it to the resource fd_my_file, all we need to do is put the resource name one space after the declaration of our syscall variant. So now each time that Syscaller will use the open my file variant, we know that it will always come back to a resource of fd_my_file. Last, we need to use the file descriptor. So we use here in the read my file that you already saw in the previous slide, and we pass it the fd_my_file file descriptor. So always we're going to read from my file. But we don't only describe syscalls. We also need to describe structs. So on the screen right now, you can see the struct foo, which written in C, which have 4 fields. And on the right, you can see the Syz'ed equivalent of the same struct. To describe a struct, we use the curly brackets that just say to Syscaller, this is a struct. We also have some other kind of brackets to do unions and other stuff. We also have the struct name. In this case, we have foo. Then we have the fields. We have the field 1, which is int32. You can see here that on the C part, we have an unsigned 32, and on the right side, we don't indicate it's unsigned or signed. That is because we just send a random input. What we need to know is that it's 32 bits. We also have the special array type, which is somewhat similar to the buffer. We declare here 32 instances of 1 byte inside the array. And we also have the pointer. The pointer, in this case, you can see is just a pointer to an int16 data. And in this case, this pointer is an input. So beforehand, we told, you saw that we declared an output buffer. In this case, we give it an input. That way, Syscaller knows to populate the input with some int16 data. We can also, of course, tell it to be an output in case this struct will be used to get information from the kernel and not to the kernel. But syscaller is a coverage-guided fuzzer, so we need to collect coverage. And inside the Linux kernel, we use the subsystem kcov. Kcov is a kernel code coverage subsystem designed to collect coverage from running tasks, and of course used by syscaller to know where its inputs got when executed, so it can generate new mutations and get for another part of the code. Let's see how we can use the kcov, what's the underlying stuff that happens. So when we build the kernel, the compiler adds this sanitizer cov trace pcp function to every basic block. So in the case of this function of the myKernfunc, we have 3 basic blocks. So when building the kernel, we'll see that it adds the call for the function 3 times. Each time the kernel calls this function, it will save the return address in which we got into the function, and will save it to another file. So if we have the return address of deadbeef, and we want to save it to the syskernel debug kcov, which is the file that the user space reads from the coverage collection data, it will be saved afterwards to this file for reading. But we have a problem with kcov. Kcov can only collect data for current running tasks. That means that if we send and execute an input, the syscall handler will know to collect the coverage data. But if this syscall handler sent some of the data for parsing in another kernel task, we won't be able to collect the coverage for that code. For that, we have remote kcov that knows how to do such. The con for remote kcov is that the kernel needs to be modified and recompiled with another kcov annotations for it to work. Okay, so we can use 2 functions. We have the kcov remote start that gets a unique remote handle. This is just an unsigned 64 integer that tells us where we should save the coverage collection. And to stop the collection, we just use kcov remote stop. And again, let's see an example. If we have this myKernel task that we want to annotate to be able to collect remote coverage, we just add at the start of the function the kcov remote start, and we send it some remote handle. And by the end of the function, we just tell it to stop. That is all for syscaller. But we told you that we're going to talk about the NVMe over TCP. So let's see a bit of an overview for that. NVMe is just a protocol used to control PCI devices, like your everyday SSD. By the years, the NVMe developers decides to create an extension called NVMe over Fabrics. This extension allows to control NVMe devices remotely. And again, by the years, they decided to do it over a TCP connection. Today, NVMe over TCP is mainly used in data centers and cloud environments, and it's a growing technology developed by Dell, NVIDIA, Lightbits, and much more, and is part of the Linux kernel since version 5.15. But we're here to talk about offense. So let's talk about the NVMe over TCP attack surface. So we get the driver gets inputs through the network over a TCP connection and parse the data it gets in kernel space. In case we have a bug in kernel space, through the network, we can get up to remote kernel code execution, which is the holy grail for attackers. And of course, let's add the two things together. Let's add NVMe into Syzcaller. To do that, we need to create three main things. We need to create a syscall, to define a syscall to send the NVMe TCP payloads. We need to define the NVMe over TCP structure. And of course, we need to open the socket to be used to send the payloads. Let's start with sending. For doing that, we just use the send syscall, and we use the variant. We created the variant inet NVMe PDU. PDU stands for Protocol Data Unit. This is just a fancy name for the payload itself. We pass it the NVMe sock, which is a predefined resource we created to get only NVMe sockets. We pass it an input pointer of the PDU from the type NVMe TCP PDU, which is a structure we'll need to describe later on. And we send, of course, the length of the PDU. The last parameter there is just the flags. We always send 0, a constant of 0, because we don't need any special flag. We successfully defined the send syscall. We now need to describe the structure of the NVMe over TCP. As you can see on the screen, we have the NVMe TCP PDU. This is a union. We didn't talk about it. If you want to read more about it, there is a blog that will be published later on today. But what we do need is to talk about the NVMe TCP data PDU. This is the structure that will get eventually to the NVMe driver with some data PDU. This is just to send the data and not any other command. The structure looks like this. We have inside the 6 fields, and by the end you can see it from size NVMe TCP data PDU size. This is a constant that been created when we built Syzcaller. This is just 32 bytes, so don't get over it. This is for the structure of the NVMe TCP definition, and we also need to open the socket. You probably guessed why I create the socket last in the stock, and that is because this is the most difficult part of the adding NVMe over TCP to Syzcaller. Because we could not just use the regular socket syscall, because Syzcaller inputs runs inside a sandbox environment inside a different network namespace. That means that if we create a socket inside the input, it will not see the NVMe driver. So we decided to create a new sandbox. But when we suggested it to the Syzcaller developers, maintainers, they didn't really like the idea. They say it's not a good practice. I guess they're right. But they suggest to use this pseudo syscall, which called a syzinitnet socket. Pseudo syscall is just a function in C that Syzcaller can look at like a regular syscall. It doesn't know if this is it runs inside the kernel space or the user space. So this pseudo syscall creates sockets inside the init namespace outside the sandbox. But unfortunately, we cannot create a TCP socket because of some checks inside the function. So finally, we decided to create a new pseudo syscall. This time, the maintainers liked the idea, which led us to this beautiful, beautiful function. We start with getting inside the root network namespace, creating the socket there. Then we getting back to our sandbox namespace and close the network namespace handle, so no one could abuse it. By the end of the function, we also making sure that the socket we created inside the init namespace will always connect to an NVMe over TCP that runs on the localhost on port 4420. And of course, we just return the socket afterwards. So we have those three things that I said we need. And when we got all of those together, we just decided to execute our fuzzer. But we didn't get any coverage whatsoever. And of course, no coverage means no bugs. That is because our NVMe over TCP works. Sorry. Okay, so on the screen, you can see the function that is responsible for getting the TCP packets that will be parsed by the driver. And by the name of the function, you can see it's a work queue function. A work queue, what you need to know is it's an asynchronic function, and in our terms is a remote kernel task, which means we need to use remote kcov in that case, and that's why we didn't get any coverage data. When every syscaller input gets executed, it will have a unique kcov handle inside its task struct structure inside the kernel. That means that every input we execute will have the unique kcov already. We don't need to invent the wheel to make a new kcov handle. But our task is to make sure this kcov handle will go from the task struct of the executed input into the NVMe driver. To do so, we dig down at the NVMe TCP IO work function and got into the NVMe T TCP try receive PDU. The names are so long. And in there, you can see that we have the kernel receive message, which is the function that gets the message headers, which is the actual payload of the TCP packet. We decided to just start the remote kcov from there. But of course, we still don't have the unique kcov handle from the original task struct. For that, we chose to use the message header struct. Again, the message header is the struct in which the packet data will be copied into. So we decided to maybe just send throughout the TCP packet also the kcov handle itself. To do so, we modified the struct message header and added the kcov handle field, in case, of course, the kernel is configured with kcov. And to use it, we also added a set kcov handle and a get kcov handle. Okay, so we needed to pass the kcov handle, but we needed to make sure this kcov handle will get into the TCP packet. And for that, we also needed to get inside the kernel receive message and check where the data is being copied. And this is inside the TCP receive message locked function. When the kernel finds the socket buffer, which is the buffer that has the packet data, it just copies the data from the socket buffer inside the message header. The beautiful thing for us, the lucky thing for us, is that few years ago, someone already created the remote kcov support inside socket buffers. That means that each time the kernel sends a packet using the socket buffer, it will always add the kcov handle of the current task struct inside the socket buffer. So all the things we thought we need to do to add the kcov handle to the TCP packet was no longer needed. We just have the Kekov handle inside the socket buffer. So we decided to use it. And we created the message header set Kekov handle with the Kekov handle from the socket buffer of the packet. That was a bit technical, so let's do a quick recap. We have an input executed by Sys executor that has a Kekov handle inside the task struct of the process. When it creates the skbuff during the sending the TCP packet, the skbuff gets the same Kekov handle. And when the skbuff data is copied inside the message header, the original Kekov of the executed input is copied into the received message header. And that way, we successfully managed to get our Kekov handle inside the NVMe driver. We just need to change this to the get Kekov handle. Of course, this wasn't so easy because the receive label here is running inside some kind of a loop in case the packet is being buffered. So we check that for every packet we get, we always start the remote Kekov collection just once, because if we do it twice for the same unique Kekov handle, some bad things will happen. So we had to put it inside this if statement. Okay, let's get to our demo that I told you we'll have. And you can already see we have a crash here. Let's go to the web UI, hit the refresh. And as you can see on the screen, we already found 6 bugs. One of them is no, it's not here, unfortunately. Okay, so we have 2 null dereference. The third one is also a null dereference that will be remote denial of service. Let's go back. And I hope you'll believe me that we had some nice other bugs. So let's conclude it all. And start with the findings. The best bug we found, the best vulnerability we found is this use after free read inside the process one work. This is actually not a use after free per se. It's more like double free that can be exploited remotely, which means we have the kernel remote code execution that got the CVSS score of 9.8. We also have 1 info leak and 3 remote denial of service. Okay, so we sent a pull request with changes to the syscaller maintainers. It got approved, and now each and every one of you that want to fuzz the NVMe over TCP can do it using the official repository. But we do have some future work. We need to send the patch with the remote Kekov changes to the Linux kernel. The reason we didn't do it until now is because we didn't test it for efficiency and reliability, and we don't want to put some nasty stuff inside the kernel. We also, of course, there is always room for improvement, so we can improve the descriptions of the NVMe over TCP. And the coverage collection. And we can add new support for new subsystems using the knowledge we now have. So thank you all. And if you do have questions, please feel free to ask. Okay.
Thank you for your presentation. How much time did it take for you to figure out how to implement a new subsystem in Syz'ed, approximately?
So the process was long. I think a few months, probably over half a year. But we did have some issues that more like issues of my thinking of how we need to do it. But I really think it could take 2-3 months, even less, if you have the knowledge for it now. So I think for me now it will take like 1 month, I guess. For everyone, it should be probably more of the same.
Okay, thank you.
Well, everybody is hungry, so. So yeah, thank you for Alon.